Okay, today we're doing standing waves. You might want to sit down for this one. Okay, standing waves. What's a standing wave? A standing wave uses interference, both kinds, right? Interference to appear still. I'm going to put still in quotes because it's not really still, but you'll see what I mean. Alright, so best example of this is basically what a jump rope looks like. Okay, back when you used to exercise with other people in the heathen ages, you used to play jump rope. Now if you have a jump rope and you only have one friend who will play jump rope with you, this one is tied to a pole, and what you do, see, look, they're having fun. You can see they're smiling. And so are you. It's only sad on the inside. Anyways, so you're going to pull the rope up and pull the rope down. Now, what's going to happen is the rope is going to be up here, and then the rope is going to be down there, and it looks all nice and stable. That's what a standing wave is. So here's what really happens when you're doing this. Alright, so we're going to give you a starting position here. So let's say you started with the rope nice and flat. You know, you'd have some slack in there, but whatever. And then you'd pull it up. Alright? So when you pulled it up, what's going to happen, this is the next frame of the video, is the wave is going to be traveling this way, right? Towards the wall. Now, what's going to happen after that is the wave is going to run into the wall, right? And bounce off of the wall. Now, when waves run into something hard like that, you know, something, the end is tied to the surface, it's going to bounce back on the opposite side. Alright, so you've seen this before if you've ever like twanged a guitar or something like that, or a clothesline, or just an extension cord. Whenever you shouldn't do it to an extension cord with electricity, by the way. So when the wave hits the end of it, the end is fixed in place, so it bounces off, alright, on the opposite side, and then the wave's coming back here. Now, what you're going to do when the wave gets to you is the wave is here, and you are going to pull it up again. Now, these waves are going to cancel out because they're both right on top of each other. Okay, so for this instant, the rope will look perfectly flat. And then finally, what's going to happen is, whatever. So this wave, I'm going to call this wave A, the first one, right? That one hit your hand. Your hand is fixed in place again, so it's going to bounce off on top. This is wave A. And this is wave B, your new wave. Your new wave is going to travel with it. So A and B are going to be lined up with each other. And it'll be a little bigger. Now, it's not going to spiral out of control because you have friction and stuff like that slowing you down. So your standing wave is going to be when the waves become interlocked with each other. All right? So then it's going to just continue the cycle over and over again. Now, in reality, your wave isn't going to be this short. Your wave is going to be much longer. You can see right here the wave is going to take up the whole length of rope. Alright, but I drew it shorter so you can see it moving back and forth. Okay, so that's what a standing wave is. Now, you can see that there's interference, and you see how it appears to be in place. Okay, so here's an example of some standing waves. Now, some things you can notice here is you can have more than one hump in the standing wave. It'll work exactly the same way. It just has additional interferences with the waves as they go back and forth and back and forth. Now there's some points that really matter here. The first kind of point, just some vocab for you, is a node. Okay, a node is when you have destructive interference. Always. Alright, so these will not move. Alright, an example of this is right here. So this is a node. And this is a node. Alright, how do we know it's a node? Think about our example before with the jump rope. It's a node because your hand isn't moving up and down significantly. It is a little bit because you're applying the force, but think about the other side, the knot on the pole. That's not moving at all. It is the exact same situation here. This is also a node. Alright, now where there's nodes, there's antinodes. Antinode is opposite of node. It's where the most movement is. Ooh. So where's an antinode? Antinode is here, because point B is going to be going up and down the full length here. It's the same thing for D. Alright? So this is going up and down the most because it's an antinode. So we'll write antinode. And the amount of nodes you have depends on how many humps you have. Right? So in this case, there are 3 nodes, and there are 2 antinodes. Okay, let's look at this one. Can you count how many nodes there are? Give you a minute. Did you figure it out yet? Okay, so there are 1, 2, 3, 4 nodes. How many antinodes are there? There are 3 antinodes. Alright, looking at this wave underneath, these 2 waves have the same amount of nodes because they have the same wavelength. Alright, they've got the same number of humps, whatever, however you want to call it. But what's different is the amplitude. Right, do you remember that from your parts of waves? So basically, these are being shaken up and down at the same rate. It's just this one is shaken up and down with more energy, if that makes sense. Alright? Okay, there's one more thing we gotta look at, and that is harmonics. So when we're talking about standing wave, harmonics is how many roads? No, sorry, no copyright strikes. How many humps there are. Okay, so there's 2 ways of naming things, which is awful. Right? This one right here is the first harmonic. We can see a picture of it. The first harmonic, it's also called the fundamental. Okay? This is the smallest possible standing wave. Alright, because you can't have less than 1 hump. If you have it perfectly flat, it doesn't count as a standing wave. Your second harmonic is when you have the next amount. The next amount is 2 humps, right? 1, 2. It is impossible to have between these, all right? There is no 1.5 harmonic, okay? The reason why that doesn't work is because the waves won't interfere with each other correctly, and it won't make a standing wave. It'll just make a bunch of gobbledygook, like if you randomly shake a wire. Okay, your third harmonic looks like this, and your fourth harmonic looks like that. You can see the harmonics match the number of humps. Now, it is also important that you are aware that these are also called overtones. So the first overtone is equal to the second harmonic. Yes, I know, but they didn't ask me when they came up with this naming system. The second overtone is equal to the third harmonic. These are the same things as each other. and the fourth harmonic is equal to the third overtone. You should be aware of both. I will try to use harmonics mostly, but I am not limiting myself to avoiding overtones. Okay, so let's do a little practice. What is the fundamental wavelength of a standing wave on a string that is 2 meters long? I'll help you out with this first one. Here's a string. It's 2 meters long. Beautiful. It is the fundamental. The fundamental is the bottomest one. So here is what it would look like. All right? I'll draw the bottom half too. Sure. So what's the wavelength going to be? The wavelength is not 2, because that's not a full wave. You cannot fit a full wave, because a full wave is up and down and back again. So here's up, here's down, here's back again. This is a full wave. How long is this full wave? The full wave is not 2. 2 is this long, so the full wavelength is 4 meters, because it's 2 meters here and 2 meters here as it comes back. You could also think about if you folded it over 1, 2, but that's more work. Don't think of it like that. It's just more trouble. Let's do another one. What is the wavelength of a third harmonic on a string that is 12? The first thing you should do is draw a picture. All right, and then try it out. Pause the video. We'll give you 5 seconds. Okay, hopefully you paused the video. A third harmonic is going to look like 1, 2, 3, like that. Now, to figure out what the wavelengths are, we know that the string is 12 meters long, so we are looking for, where's a full wave? A full wave is not that much. A full wave is this much. Alright, so this is a full wave. You can see it right there, up, down, and back again. So how long is that? Well, it's 2/3, right? Because I need 1, 2 of these humps out of 3. So 2/3 out of 12 is 2/3 times 12, which is going to be 8 meters. All right, ta-da. Are we feeling okay with that? We got one more to do. Well, the first overtone has a wavelength of 3. What is the length of the string? All right, pause the video, draw it, and see if you can come up with an answer. Okay, so here, first overtone means the second harmonic. So it's going to look something like that, beautifully symmetric. Well, if this has a wavelength of 3, right, lambda is equal to 3, so how long is the string? Well, this is a full wave, so L is equal to 3. I should put a unit on there, meters. Ta-da! Alright, so we're going to do a little practice on this stuff, combining it with yesterday's stuff. Tomorrow we're going to do some review and get you ready for a quiz next week on all these wave things. And that's your plan. Like and subscribe for more videos coming your way.